So let's look at some of the mathematical manipulations which are going on in the OFDM transmitter and receiver. Remember, key component, FFT. So we have on one side of the transmitter side an inverse Fourier transform, and on the other one a Fourier transform. And I'll be trying to show you about the idea of what's going on in this OFDM transmission. So we have data we want to transmit. And the data, stream of, let's say this is the binary case. Here I have a stream, 52 bits for the 802.11 standard. And I'm assuming that I just have binary keying now, so make it really, really simple. And I take this stream and I break it up, and I don't think of each one as going on the total frequency domain. I think of each one of these bits being assigned to one subcarrier. The next 52 bits will be assigned, again. That'll be the second data stream. Before my illustration, I was using 8. Here it's 52. So what happens is I take this data, is plus or minus 1, and I put it into my vector. These are mathematical manipulations. So I have this vector. Think of this as a vector in MATLAB. I'm going, what is this, 64 element vector. And this 64 element vector, I'm going to be doing a Fourier transform on. And so I have some that I'm not using. I put in zeros there, and I'll discuss about why I wouldn't be using them. And then in the ones I am going to use, these are going to represent the data where I'm going to transmit information. And for instance, I have +1 here, so I put a +1 here. -1 is a -1. I'm only plotting the amplitude. I'm not plotting the phase, but these are like out of phase from one another by 180 degrees when it's plus and -1. So I put in a +1, -1. I put my data into this vector. What do I do with this vector? First of all, what do I interpret this vector to be? I interpret this vector to be a frequency domain vector. Frequency domain. Okay, frequency domain. What am I going to do with this vector? And here I just show them all packed up, all used. Well, I take that frequency domain vector and I turn it into a time domain vector. So I take the inverse Fourier transform. When I take the inverse Fourier transform, it's no longer going to be this nice binary, only two values, plus and minus 1, amplitude always 1. That's not going to be true anymore, because I do the FFT, and the FFT is going to leave me with some form that doesn't look like there's no obvious modulation going on in there. But this becomes my time domain signal, and this is the signal that I will be transmitting from my antenna. So I take my block of data, I run it through a DSP block that calculates the inverse Fourier transform. I get out a vector. This vector, I assume, are the samples that I'm going to send to my transmitter. So I do a digital to analog conversion, and I send it over the wireless link in the case of 802.11. So if I look at the spectrum looks something like this. Looks like Bart Simpson's head. I have something that looks very steep, because this was a pretty narrow band signal, so that when I look at the wide scale, it looks like it's a very steep ascent. These are a whole bunch of subcarriers which are lined up one another for my transmission, because if this is what I send to my antenna, then if I looked in the frequency domain, it looked like this, a bunch of little narrow band signals. And so this is a typical OFDM spectrum. Now, try and think of what's going on. If I think of this, if I'm trying to figure out what's happening in an OFDM signal across time and across frequency. So let's see if we can figure out what's going on in this complex diagram here. First of all, let's look at which scales we're looking at. So here we see it says frequency. So this is the axis where frequency is changing. And then here is the axis where time is changing. So if we look at first at the time axis, you'll see that there are some guard times which are put in place, and that there are transmissions during a given interval of time, and then another guard band where it's quiet, nothing's being transmitted, and another one. Now, this represents all the different values of voltage that could be being transmitted by this antenna. And I see that in this plot is sort of these different colors. They're just supposed to, it's varying in time. So I have some things that's varying in time, and we call these OFDM symbols. In this one OFDM symbol, it's like I have all of these 52 bits that I was going to transmit. I had put them all into a vector. I calculated the IFFT. I got a time domain signal. Now I transmit that time domain signal, and I call that, well, one OFDM symbol. And that one OFDM symbol, it contains all of these bits. But I can't sort of say which bits are where because it doesn't make sense that way. The bits are isolated in the frequency domain, but in the time domain, they're kind of all mixed up, which is what we're trying to see in this illustration here. So I send the symbol, and then I have a little guard band. That guard band is where I make a concession to the multipath delay spread. So this is long enough for the delay spread to balance out. But of course, it's not a delay spread that I need to tolerate for one bit transmission. It's for the whole 52 bits, so it's not a very high overhead. The reason I have this is to maintain orthogonality, to keep my cyclic, cycles of the different frequencies to be all finished during my transmission. So that's the reasons for these guard bands. And now let's look at what's going in the frequency domain. Well, if I looked in the frequency domain, now I'm looking at a cut across FFT, across the frequency domain, and there I'm seeing my subbands. I'm seeing my subbands, and that's why you're seeing one color, because that represents like one bit. Because if I go back here, during the whole transmission time here, in the frequency domain, the symbol is not changing. So although the time domain signal is going every which way, in the frequency domain, my symbol stays the same during the whole symbol transmission, which is why we get these individual colors that are staying the same when I look at the axis on the frequency axis. And so these represent all of the occupied bins, FFT bins. So when I put in a data value here, that represents what's going on that frequency subcarrier. So mathematically, it's just a symbol and a position on a vector. Then I do the inverse Fourier transform. I get a time domain signal. The time domain signal is sent over the antenna. So here's an antenna. I'm sending this time domain signal to another antenna. And this time domain signal that I'm actually transmitting has these frequency characteristics. And what I do in between here is to observe what I'm seeing along the way. And so I'm breaking it up into OFDM symbols, a certain given time, and during that time, nothing is changing in each one of those frequency bits. So during this time here, there's this one vector of time symbols that was being transmitted here, and then I'm showing it being any old thing. And so these are very varying, but during if I look along the frequency axis, we can see in each one of the frequency bins, there's some value, but it stays the same all during that transmission. And of course, the relationship between these time domain and frequency domain is just the Fourier transform relationship. So let's look at the implementation of the OFDM. What's going on in the transmitter and the receiver. And so we see here a block diagram of the different steps that we're going through. The first thing we do is we have our bits coming in and we do a series to parallel. And this means I'm taking my sequence of bits like I have up here, and I'm putting each one in a position in this vector. Then I take this vector and I modulate it. So if it's QPSK or if it's 16 QAM, I take a selection of, if it's QPSK, I take 2 of those bits and I turn it into an IQ coordinate. If it's 16 QAM, I take 4 of those bits and I turn it into an IQ coordinate. Now these IQ coordinates are what are being transferred into the FFT. So in that BPSK, it was plus or minus 1. So each bit here went into either a plus or a minus 1. And if it was QPSK, it would be 2 of these bits would get together, and then I would be putting in, you know, plus 1 plus j, or whatever the coordinates are for the bit pair that I'm sending. So here, in all of these n subchannels, I have this vector full of complex numbers in general. We saw the BPSK, which was not complex, but if it's a higher order modulation, it would be a complex coefficient. And I just have formulated this vector. I take that vector, I put it into an endpoint IFFT, n being the number of subcarriers, and being the number of data symbols that I have gathered together into a vector. Now I have the time domain signal which comes out of this IFFT, and I go from parallel to serial again so that I can get just a time series, and that time series is sent for transmission. Goes through a multipath channel, and I come out and I do the exact same manipulations in reverse at the receiver. So I might have to filter, eliminate some noise, do an analog to digital conversion because I'm doing everything in DSP. I have to use the digital form, series to parallel. Now I go from time domain into frequency domain, so I use a fast Fourier transform, and now I've got into those symbols that were transmitted, and then each one of those vectors coming out, each one of those elements coming out of the vector of the Fourier transform, each element of that vector now corresponds to the IQ coordinates for the symbol for a particular subcarrier. And so now I've got my data stream back again. There is a couple of steps going on that I sort of glossed over, and now I'm going to give you a couple details a little bit more on what is needed for this implementation. The first one is called the cyclic prefix. Cyclic prefix corresponds to that time that I said was a guard time. So during the guard time between OFDM symbols, so I've gathered together a whole bunch of bits in this whole vector. That comes out, that vector of time domain samples I call an OFDM symbol. And between them I have a little guard. And this guard time is used for a cyclic prefix. And basically the length of that time is determined by the delay spread. So the guard interval is about as long as the delay spread of the channel. And that allows me to be sure that despite the reflections in the channel, that I will get a full period, if you will, of the carriers. So for each one of the carriers, I just tack on to the end of my OFDM symbol a repetition of the oscillations in the carrier so that my orthogonality is maintained despite the fact that there is a little bit delay spread in the channel. So, last step before we go into the transmit over the last step in the digital signal processing is to add the cyclic prefix. And at the receiver, the last step is to remove that cyclic prefix. It has no data on it. It's just meant to preserve orthogonality. So we add it on, strip it off, And then the other part that I guess I haven't mentioned is that there is some equalization. So here is this equalizer. The whole point was to avoid an equalizer, but this equalizer is super simple. It's a one-tap equalizer. It's just doing one correction, and I'll explain to you how we can do that equalization very, very simple. And so it's important to realize that the reason that we turned to OFDM, at least in this argumentation I'm giving you now, is to avoid intersymbol interference. And we're avoiding intersymbol interference, but we still have to equalize a little bit the channel, not to avoid ISI, but just to do good coherent reception. So that's really what this is about, not ISI related, but reception related. So this one-tap equalizer that I mentioned for OFDM is used to compensate, to achieve coherent detection. So the main reason we have it is to be able to do coherent detection. Remember, there's one oscillator. Even though I have many, many subcarriers, there's really one oscillator. So what does that mean, one oscillator? I said that we have this antenna for the transmitter and receiver. And normally there's some carrier, right? So maybe this is Wi-Fi, and I'm doing 802.11a, and it's a 5 gigahertz carrier. So that when I come out of my OFDM inverse Fourier transform with my time domain signal, what I do is I multiply this by this 5 gigahertz carrier. And so all of these different subcarriers, well, the center frequency becomes 5 gigahertz, and then in each one of these I have some subcarrier that I'm using. But the important thing is that when I send this transmission, there's one physical oscillator which is at 5 gigahertz, the center frequency. There's not an oscillator, a separate oscillator for each one of these subcarriers. So that means that the phase that I have to track, there's really only one phase that I have to track, which is physically varying. So that's good. That keeps the complexity down. But there are channel effects. Okay, the channel effects, I was talking about each one of the multipath returns could have a change to the phase and a change to the amplitude. So that means that although there's only one physical oscillator, there are the channel effects that really I should be equalizing in order to have good coherent reception. So it's, again, not so much to combat ISI, which should not be high because I've already gone to these long symbol periods. But there is some variation in this main phase, which is changing a little bit maybe from carrier to carrier because of the channel effects. So the phase may vary with subcarrier, and that is the point of this invert the channel, is just to take care of this phase change introduced by the channel. So now let's look at how we can easily equalize the channel without having to do a whole lot of processing. And so what I have here is a plot of the time domain on one axis and the frequency domain on the other axis. And think of each one of these frequency domain rows being one of the subcarriers. And this is the time of one OFDM symbol. So what I see here are, you see the code here, when it's white, it's a pilot. When it's empty, it's data. So most of the squares in this time frequency domain plot are dedicated to data. But there are a few of them which I reserve for doing channel estimation. And this is a bit more explicit channel estimation. So I'm going to send a pilot. What does it mean when I send a pilot? When I send a pilot has no data on it, no modulation on it. It's just the pure carrier, a pure tone, a pure carrier. That means that it's very easy to just read directly what is the phase. There's no modulation. It's not like it's changing from one phase to the other depending on whether I'm I'm modulating with which coefficient in the constellation that I'm sending. And no, it's constant. So it's very easy to read. So I could directly read at the receiver what was the attenuation, if there was some, and what is the phase rotation, if there was some, on this particular channel. So you can see I have different strategies. If I'm interested in variation across frequency, so suppose that although there's only one physical oscillator and there should only be one rotation of the phase, well, because of the channel effects, maybe it'll vary a little bit from some carrier to subcarrier. So every now and then I'm going to put this is the main estimation of phase that's going on here. This is the main estimating the phase of this oscillator at the transmitter. So I have one channel for frequency that I reserve just so that I can keep an eye on that oscillator and track what's going on with its phase. And it might be drifting with time, so like all of the time I'm keeping this one channel just to observe the oscillation, the phase rotation on that oscillator. Then every now and then I'm going to have a look at a subcarrier. I'm going to assume the ones right next door probably don't have much change in the phase, but every now and then I get far enough away, maybe the phase has changed significantly, and I observe what it is because it's a pilot and there's no data on it. And I do that every now and then in the frequency domain, and because it could be changing with time, I do it every now and then in the time domain. So that's why I sort of tiled this area with different pilots, and the pilots allow me to easily invert the channel. I don't really estimate the channel, I just observe it. And then I apply the inverse of it. If this introduced a 5-degree rotation, I just multiply by a -5 rotation, and I've gotten rid of it. And in all of the neighboring ones, I assume that it's the same and do the same simple channel inversion. So this is what's going on in the transmitter. I'm sending like the same modulation format, the same power, but at the receiver, because of the channel, things get messed up, but then I can sort of compensate for it because I have these tones which are letting me figure out what's going on. And of course, I can't improve the signal-to-noise ratio. The noise is always there. I can try and say, well, I know this one is attenuated, so I'll beef it up. I'm going to beef up the noise too. So we can improve this signal-to-noise ratio, and we get a really bad hit. Well, maybe I'm going to get hurt there, and I'm going to lose something. I mentioned that's just what happens, and I have to do a retransmission. So from time to time, you lose a subchannel. The FFT is nice because it's high performance, it's inexpensive, and I can choose sort of the complexity, if I will, of the IFFT, because the more carriers I have, the more subcarriers I have, the more complex, but the more ideal that might be the conditions for my estimation, etc. So it's a trade-off, and that you'll make your decision on what you can do, and there's a whole engineering approach to how you would choose how many subcarriers you would use, depends on the channel, etc.